Welcome back to more discussions of the application of the normal distribution and assessing normality. Let's begin by discussing how much time you might spend in a Wendy's drive-thru waiting for your food. Okay, so the mean time spent in a Wendy's drive-thru, according to QSR magazine, is 138.5 seconds with a standard deviation of 29 seconds. So my question to you is this. Let me switch colors here. Okay, what is the probability that a randomly selected car will get through Wendy's drive-thru in less than 100 seconds? So I'm asking about the probability that X is less than 100 seconds. Now the problem setup does state that through the QSR magazine's research, the data was approximately normally distributed. So we can set up our data, set up a distribution based upon a bell curve, a normal distribution. So when we're looking at this, what we will see is, let me choose something will show up, a mean time of 138.5, this is in seconds, and then I need to add 29 seconds for each of those standard deviations. Now, there I've labeled my mean and my standard deviations, and yes, I do miss having you to check me on your calculators. The mean time spent in a Wendy's drive-thru is a continuous random variable, and by labeling this bell curve, this normal distribution, as I have, it is representing the original data. So now I just need to compute the z-score for the time of 100. Before I do that, let me go ahead and mark that value of 100. So let's compute the z-score. The way I'm going to do that is using my z-score formula. I'm going to take the number in which I'm interested, 100. I'm going to subtract 138.5, which is the mean, from it, and I'm going to divide by the standard deviation. Z equals negative 1.32759. A good question to ask now is, how many digits do I have to report for this? And the answer depends upon the table that I'm about to show you. You will find a table similar to this in the back of your book in the indexes. It's Table 5, the standard normal distribution, that's how it's titled in your book. All right, the table will be read in the same way, although it looks slightly different. Notice the note at the bottom of the page here. It's a very important note. The probabilities, or the areas, given in this table represent the area to the left of the z-score. So in this first drawing, the z-score in which you're interested is there, and the probabilities indicate the shaded portion. Even if the z-score is above the mean, as it is in the second half of the table, it's still giving you the area to the left of the z-score. Now we will need to zoom in on this a little bit. So we are interested in a negative z-score. So we need to talk about how to read this table. If you notice, down the left-hand side, we have two-digit numbers, and those are probably a little bit blurry for you, a little bit difficult to read. But they are a ones digit and a tenths digit. And we are looking at, with our z-score that we've calculated, a negative 1.327, blah, blah, blah. Okay, well, there are only two digits shown on the left here. There is a ones digit and a tenths digit. But if you look carefully along the top of the page, you have numbers that have no ones or tens digits, but they do have a hundredths digit. And if you combine that hundredths digit with the other number going down this column, you will have a three-digit number. And so let's convert our z-score to just three significant digits. So let's make it 1.33. we need to round up because of the 7 that is following the 2. When you are reading this chart, make sure you're aware that going down the column and across the top, combining those numbers, gives you your z-score. And that z-score is a reference that lets you enter the table and find the area to the left of the z-score. So I'm going to go into the table at this negative 1.3, and I'm going to keep going over. That's negative 1.30, negative 1.301, negative 1.302, and negative 1.303. So I've gone across that column, and across that row, and down this column to find my number. So now what I have found is the area, or let me make that a little smaller, area for the z-score of negative 1.33. So I'm just writing that z-score down below. It's commonly not done at all, but it helps me remember where that area came from. It came from the z-score. I used the z-score to read the chart, and now I know that the area to the left of the z-score of negative 1.33 is 0.0918. And now you can put away your chart for the moment. So we have an area of negative 1.33. That's the area, whoops, let me get out the correct utensil here. That's the area to the left of 100 seconds. That would be all of the times that are less than 100 seconds. That's 100 seconds of waiting in line for that single at Wendy's. And you can just write that probability as 0.0918. That's perfectly acceptable. But you know what? I like to think about it like this. 9.18% of the time, when I go to the Wendy's drive-thru, I will probably wait less than 100 seconds. That means most of the time I'm going to be waiting more than 100 seconds. Because think about it, that's less than 2 minutes. That's ordering and getting your food. That would be really quick. Okay, let's check out another case. Or let's calculate what the probability is that a randomly selected car will spend more than 160 seconds. So the probability that X is greater than 160 seconds. So I'm looking at approximately here being 160 seconds. Now remember, we're looking at the probability that the time spent is greater than that. Okay, so remember that point, because first we have to calculate a z-score before we can do anything else, and then we're going to think about what the area above our value means. Okay, so if z, for calculating z for 160, we take 160, subtract 138.5, because that's the mean, and we divide by the standard deviation. And would you look at that? As soon as we do that, we no longer need the values along the bottom of our graph, because we're no longer graphing x, the random variable x. We are graphing the random variable z. We have standardized the distribution by referring to our z-score. And the z-score equals 0.741379, etc., etc. Remember, we're only going to be using these 3 digits when we refer to our z-score chart, our z-table it's called. Because I see that our z-score is positive, I have only included the positive half of the chart now, and before we look for the area for this z-score, I want you to take a look at the beginning of the chart, because this first column and row together give us nothing. Well, they give us 0.00, which is the z-score for the mean of all the data. And as you see, it's a little hard to see because it's small right now, the area is this. That means that 50% of the data is less than 0, the z-score of 0, which you already knew from the empirical rule. But 0 is not the z-score we're interested in. We are interested in 0.74. So here is 0.7 and 0, 1, 2, 3, 4. So we're coming over this way and down this way, and our value is 0.7704. So we have the area. I'm sorry, for some reason I'm reverting to cursive tonight. Z-score of 0.74. So that area is 0.7704. We are now done with the chart for the moment. All right, so we have that z-score and its associated area. But wait a minute, remember from the chart that the area given in that z-table is the area below the value of interest, below the z-score. So at this point, we have to remember that the area under the curve, the entire area, is equal to 1. And if we now subtract the area to the left of the z-score that we are interested in, then we will get the area under the curve above the z-score. And that will be 0.2296. So this is not the area we want. We actually want the area greater than 0.745 for z greater than 0.74, and that is 0.2296. Okay, so what does that mean? Well, we got what we were looking for. We were looking for the probability that someone waits greater than 160 seconds in the drive-thru at Wendy's. Another way to say what we just found is that as a proportion, we could say, let's round it to, instead of, let's see, here's the decimal, convert it to a percentage, and you get 22.96%. Let's round it to 23%. And I'm rounding it to 23% because it's getting late and I'm stumbling over my words, and that's easier, okay? So 23% of the people waiting in line at or going through the Wendy's drive-thru will be there more than 160 seconds. Another way to look at it is the probability that you will be in the Wendy's drive-thru for greater than 160 seconds is 23%. Well, since you are obviously a randomly selected driver and don't sit around studying the wait times at Wendy's drive-thrus until today. More information about Wendy's drive-thru wait times will be in the next video. See me then.